Welcome to the 14th lecture of Optical Sensors course. Until now we studied what are surface plasmons, and we also studied optimized structures for producing surface plasmons at a metal dielectric interface, and we optimized the film thickness to be around 50 nanometers. And then we also studied different modalities how to use it for sensing. Now we will move to something called localized surface plasmons, which are basically plasmons in metallic nanoparticles, where the size of these nanoparticles are much smaller than the wavelength of light, and we will see how to use them for sensing applications. So, what I am talking about is metallic nanoparticles which are much smaller than the wavelength of light, like silver and gold nanoparticles of say hundreds of nanometers or 30, 40, 50 nanometers, something like that. But this is something very interesting. It has very beautiful optical properties, but it was in use very long back actually. And for example, this Lycurgus cup was made by Romans in around 4th century AD, you see, and it is so beautiful that you can see that in the reflected light it appears to be green, but if you put a small source of light inside, say LED, and turn it on, in the transmitted light you will see it red. Another example is these kind of glasses, for example, the Labors of the Month one, which is in Norwich, England, and it has ruby color, which is actually because of nanoparticles, gold nanoparticles. So, ancient stained glass makers were the first nanotechnologists. So, they used to have small sized particles dispersed in glass, and then they could stain the glass using the optics of nanoparticles. It did not contain dyes. Okay. So, that is the beauty. So, what was actually that, for example, they also knew that by placing small amounts of tiny nanoparticles in some particular fashion, they can create various colors. For example, these stained glasses, they are not having any dyes, they do not have any dye. All the color which is appearing here is because of nanoparticles. While refluxing these glasses, they will add precursors of metal, and that will turn into some nanoparticles in the molten stage, and then they will cast it like that. So, for example, here a 25 nanometer nanoparticle of gold appears red in reflected light, while 100 nanometer it shows yellow. There are different colors because of different sizes and shapes. You can see that ancient glass makers, they were not very accurate. They did not have this idea what they knew that okay, if you change in these proportions you will see different colors, but they did not know that how to control these optical properties, not very precisely. Okay. So, that is a matter of study in nowadays. I mean last 30-40 years people have been using it at large scale to study the optical properties when the size goes down, and how to use it for different applications. So, plasmon resonances of metal nanoparticles are basically quanta of charge density oscillations of metal nanoparticles. So, you can experience a metallic nanosphere as shown in the picture when it is subjected to a varying time varying electric field. What happens actually that if the electric field is pointing in upward direction, the electron cloud will slightly shift to the downwards direction. So, leaving behind a dipole here, we will solve for it analytically. Dipole pointing in this direction, electric field will be in the opposite direction, and if it is varying at a frequency of say omega, then this dipole will also be oscillating at a frequency of omega. So, they get excited, this kind of oscillations when the frequency of the incident light becomes equal to the oscillation frequency of conduction electrons, and this phenomenon is attributed as localized surface plasmon resonance. This resonance frequency as well as the absorbance, because when there is a resonance, light will get absorbed by these plasmons. Okay. So, you will see an absorbance. This absorbance as well as the resonance frequency is highly dependent on the size, shape and environment of the nanoparticles. So, suppose you have a sphere, now if you take a triangle of the same material, it will have different resonance frequency and absorbance. Now, it was in air and then you put some water around, the resonance frequency will change, the absorbance will change. So, this is the property which we will use for sensing, because when you change the environment, basically it changes the resonance frequency. So, by measuring the change in the resonance frequency, you can say that how much change in the environment. Environment means when we talk in optics, it is change in refractive index primarily. So, we will arrive to that expression. So, but there are certain advantages. Now, we studied propagating surface plasmons, and now we are talking about something called localized surface plasmon. So, it has got certain advantages, that one has got certain different advantages. So, every process has advantages and disadvantages. First advantage here is that since this LSPs are confined to the nanoparticle, the electromagnetic field gets extremely enhanced in the local environment of the nanoparticle. That was happening in propagating surface plasmons also. You were getting enhanced electromagnetic field about 100 times. If you remember, Ex square is of the order of about 100 by E0 square, if we say E0 is incident electric field. So, but in this case the particle is still gets much smaller. So, you get enhancements of the order of around 10 to power 4, 10 to power 3 to 10 to power 4, maybe more 10 to power 5, 10 to power 5, 3 to 10 to power 5 or even more depending on the configuration. So, it gets enhanced. Most important thing is that it can be excited directly by shining light of appropriate frequency. Thus, there is no requirement of any phase matching technique. You remember that when we studied surface plasmons, we used to have a high index prism which was required to enhance the wave vector of light incident at the interface. But here it is not the case. You have a bottle of nanoparticles which is a colloidal solution, you simply shine light on it like this and you can excite surface plasmons there. So, also it does not require any polarized light beam if it is spherical basically. If it is say elongated, you will see that it changes bit but not much. And most important thing is that it can also be used for biosensing, because it employs silver and gold, and I told you that it can be used for sensing. So, we will see. So, let us consider LSPR in metal spheres, and to solve it what we assume is that the nanoparticle is much smaller than the wavelength of light. So, suppose our light is around 500 nanometers in wavelength, and then this particle we consider around 50 nanometer, much smaller than the wavelength of light. So, we can approximate it as if the electric field which this metal nanoparticle is experiencing is almost constant. That is why we write it quasi-static approximation. That this problem can be seen as a nanoparticle, nanosphere. For example, I have taken a sphere because it is easy to solve for this, and we consider that it is put in an electrostatic field of E0. The radius of the nanoparticle is r, the metal dielectric function is epsilon m, that is epsilon m1 plus I epsilon m2, we already know that. Epsilon s is the dielectric constant of the medium which is surrounding the nanoparticle, and let us say that at point P I want to know what is the electric field at a distance r and angle theta. So, if you want to solve this, then what we can do is that once we solve it analytically for this electrostatic problem, then we can introduce the time varying part, omega part, and we can see that how it behaves. So, we can solve it using Laplace equation, then we can evaluate what are the potentials, and then we can take a derivative of it to get the electric field. So, since it is azimuthal symmetric, the general solution can be given in terms of Legendre polynomials, okay, where L is the order of the polynomial. So, you can write the potentials in the inside and outside the sphere as a function of r and theta, and you apply these boundary conditions to arrive to this relations, right. These are the potential which you get after solving these equations. Now, you take a derivative of it, you get the electric fields like this. There is something very important here, the outside one you get this term, which is when we solve for a dipole term, you see P is the dipole moment of that dipole. So, what happens actually is that you have this sphere, it seems that there is a dipole sitting at the center, dipole P in this electric field, and this dipole has certain role, we will come to that. So, in terms of polarizability alpha, the dipole moment can be written in terms of incident electric field, which is this thing. So, alpha polarizability comes out to be this, and you see that this shoots up, becomes very high when this term is close to 0, close to 0. So, when this term is close to 0, you arrive at the resonance condition, that is called Prolate condition, and at that point you have enhanced electromagnetic fields. So, for example, in this silver nanoparticles you can see that if the dipole is oscillating in this direction, the electric field enhancement is in this direction, that we already solved for, and I already showed you that if you have a dipole oscillating at an angle, then along its axis you do not have any radiation coming out, while at 90 degrees it will have maximum radiation coming out. So, this is the polarizability and electric field for static field when the sphere is put in static field. Now, you add the term. So, if you had like E is equal to E0 e to power I omega t term, then P is equal to, again it will be P0 e to power I omega t. So, there will come a frequency term. Okay. So, it will become an oscillating dipole, an oscillating dipole will radiate 90 degrees to its axis. So, if we consider now polarized light, suppose the incident light is polarized vertically and we are measuring using a detector at an angle theta, then the ratio of scattered and incident intensities is given by this relation, where alpha is the polarizability which we derived already. For horizontal one, it is a function of cos square theta to the vertical one. So, this is also a function of polarizability, you see they both are a function of polarizability. So, if we want to see what is absorption and scattering, then we need to know the absorption cross section and scattering cross section both. and this was a function of alpha, this is also a function of alpha, and they added together are called extinction. So, extinction cross section is given by absorption cross section plus scattering cross section, which is almost this term. So, experimentally it is very easy to determine. Suppose you have a vial of colloidal nanoparticles and then you shine light on it and then you get the transmitted light and your reflected one. So, from that one there will be some light lost because of absorption and scattering. So, that you always can calculate. If there is no reflection coming out, then it is 1 minus transmission, and if there are reflections also, then it is 1 minus reflection minus transmission. So, you can always calculate extinction, that much light got extinct because of this nanoparticles, and that is a characteristic which people see while doing experiments also. So, they both depend on size and shape. I will come to that, but what happens if you take an anisotropic nanoparticle? Anisotropic means all the dimensions are not the same. So, for example, if you take a spheroid, be it prolate or oblate, you see that one of the dimensions is greater. So, A is for example greater than B and C. So, it becomes kind of spheroid. Ellipsoid when A is not equal to B not equal to C. So, this becomes like an egg, okay. And what you see is that alpha is now a function of j indices and they can vary. So, if M is the medium surrounding this, actually it should be S when later on we will see, and if you have different dimensions x1, x2, x3, then you have to have a geometrical factor which also plays a key role in determining the resonance. So, for spheres it was very simple that you put a x1 is equal to x2 is equal to x3, but here you have to have a geometrical factor which will also play a key role in determining the resonance and extinction. So, for example, to summarize it, we can write extinction with this equation 9 omega by c into V. V is the volume of the nanoparticle, epsilon s is the dielectric function of the medium surrounding the nanoparticle. So, suppose this is a nanoparticle which epsilon m and radius r, and this is the dielectric function of the medium which is surrounding the nanoparticle. So, suppose your nanoparticle is dispersed in water, then n will be the refractive index of water and epsilon s is equal to n square, that will be the dielectric function of the medium surrounding it. Okay. And this term which is get multiplied to this one. So, you see here that this epsilon m which is the metal dielectric function is a function of omega and r. That means, if you change the size of the nanoparticle, that metal dielectric function itself changes. That is something size dependence of the metal dielectric function has to be considered here. Second thing is that it is a function of omega also. Omega means it is a function of wavelength. So, its dispersive character is also something which will determine the sensing part. We will come to that. So, absorption plus scattering can be written as this equation, and the resonance condition is given by this. So, here when this term becomes close to 0, let us say that epsilon m1, epsilon m2 is kind of negligible. So, if we consider it to be negligible, then this one is playing the major part, and when this comes close to 0, you have a resonance. So, if we summarize this omega p terms for plasmons, we can see that for a sphere it comes to be like this, and ellipsoid it is like this. So, we arrived here, we calculated the asymptotic values there, and if you want to solve for it, say for metal. So, we know that epsilon metal is equal to roughly 1 minus omega p square upon omega square. So, let us say it is omega p b, omega p square minus omega square, and the resonance occurs when epsilon m is equal to 2 epsilon epsilon s. So, let us say this is 2 epsilon s is for sphere. For other shapes it will be different. So, for air epsilon s is equal to 1. So, epsilon m is equal to minus 2. So, let us put here minus 2 is equal to 1 minus omega p square by omega square. So, actually it was omega p. So, if you write it like this, arrange it, then it will be omega is equal to omega p by root 3. So, what happens actually is that, let us say that it is omega p b. So, omega p will be omega p b. That means that for metallic nanospheres, the plasma frequency becomes 1 by root 3 of bulk plasma frequency. So, suppose you have a bulk piece of metal, the bulk plasma frequency it will have around 10 to power 16 or so, but when you form a nanoparticle from this bulk piece, its plasma frequency itself changes to 1 by root 3 of this value. So, that is why you are getting something like this here. If you have other shapes, then it will be a function of that shape. So, if we write it in terms of, so omega p was omega p b by root 3, this implies that lambda p will be under root 3 lambda p b. That is what we have written here. This is called extrinsic size effects. It is not dependent on the size of the nanoparticle. It does not say, it says that okay, you had a bulk piece of metal, it has a plasma frequency of omega p b. Now, we made a nanoparticle out of it, it became omega p, which is 1 by root 3 of that, or in terms of plasma wavelength it will be like under root 3 times. But it does not tell you that if the nanoparticle is 10 nanometers or 20 nanometers, it does not change with that. That is why we call it extrinsic size effect. Also, this lambda c, if you remember this term epsilon m was 1 minus omega p square upon omega square plus omega c square. If you write omega c in terms of lambda c, that the decaying function was there, that is lambda c. Lambda c is dependent on the radius of the nanoparticle. You can see about these things in this kind of publications, and the bulk one is like this, and if you apply the size corrections, you can still go beyond that for different sizes. So, if you want to use it for sensing applications, say for example, so I have written this the same expression now in terms of lambda, rather writing in terms of omega, because now we are going to measure the wavelength here. And if you plot the metal dielectric functions as a function of wavelength, so I am just plotting epsilon is equal to epsilon m1 plus I epsilon m2, and I am plotting this and this as a function of lambda. So, here is epsilon, the red curve is the real part, the black curve is the imaginary part. Now, I take a medium which has dielectric function epsilon s, which is surrounding the nanoparticle. What you see is that for epsilon s1, this will be intersecting here. This is the condition when you have resonance. So, this is the resonance condition, and at some value of lambda 1, it will be resonating at epsilon s1. Now, you change the dielectric function, say suppose it was water, then you added sugar to it. So, it becomes epsilon S1 to epsilon S2. Now, you have to satisfy it at lambda resonance 2, only there it will be intersecting with this curve. So, when you change the dielectric function or say in terms of refractive index, say epsilon S1 to epsilon S2, basically there was a shift in the resonance wavelength from lambda resonance 1 to lambda resonance 2. So, by measuring this change in lambda, you can say that how much change the surrounding dielectric function occurred. This is how you use it for sensing. So, we have plotted here the extinction cross section as a function of wavelength for different nanoparticles of different sizes, and also we are changing the now the dielectric constant of the medium which is surrounding it. So, it is actually epsilon s, and you can see that for any nanoparticle of say let us say that nanoparticle of radius of 5 nanometer and dielectric function 1.75 nanometer, you can see a peak in the extinction. That is how it is characterized, and the resonance is here, the maximum value of the peak that gives the resonance wavelength. So, this is lambda resonance for 1 or A. Now, you change the diameter say from 5 nanometer to 10 nanometer, you do not see much difference in the resonance wavelength, because lambda Pb is not a function of radius, it was lambda c. So, the extinction cross section means the power will change, but it is not affecting the resonance wavelength essentially. However, if you change the dielectric constant of the medium which is surrounding the nanoparticle, so if you change the refractive index around, basically you see that once you increase the refractive index, it shows a red shift, with an increase. Okay. So, that is how you use it for sensing. If you take Prolate spheroids of silver, which has L and S at different values, and you can see that you have two resonances, one is here, another one is here. So, you can tune the resonance where it resonates by changing the polarization. So, you can know that which is long axis, which is short axis, and then you can tune the resonance according to the spectral range you want to work on. That is the beauty here. If you want to study for oblate spheroids, you can see that for the short axis you have these ones, and the long axis you have longer resonance wavelengths. So, this is absorption for the long axis. For the same sphere, it will have two resonances, one around the long axis, one along the short axis. And by measuring these both, you can say that you can use it for sensing again by choosing different polarizations. So, if you have this nanoparticle and you want to excite this only LSPR, you shine it with this kind of polarization. So, it will not have this short axis resonances, but if you choose any random one, it can always be resolved in two components, horizontal and vertical, and then you can have both the resonances. So, if you want to have for Prolate spheroids more exact calculations, you see that for each value of these ratios you have two resonances, the black curve, these curves, okay, and the other one is quite broad in nature. So, by choosing wisely, you can use either of this or this for sensing applications. Okay. So, let us summarize this talk. So, today we discussed what are localized surface plasmons and showed some historical examples like the Lycurgus cup and stained glasses, and then we derived an analytical expression based on quasi-static approach to solve LSPR theoretically, and we studied it for both spherical and anisotropic nanoparticles. And then we studied also that how to use it for sensing. So, you have extinction cross section for the nanoparticle, and from there you deduce this resonance condition which depends on the size shape and the environment. Environment means the refractive index of the medium surrounding the nanoparticle. And then we saw that for different ratios and different refractive index of the medium surrounding the nanoparticle, it had different resonance wavelengths. So, by measuring the change in the resonance wavelength, one can say that how much change in the refractive index occurred. So, that is how you use it for sensing applications. In the next talk, we will study the field enhancement due to these nanoparticles, and we will try to see that if we can use it for any further applications. Thank you.